Today we're on the Chem 1 Chapter 6 packet, and we're going to talk about how the elements are organized on the periodic table. We're going to realize that the periodic table has a really amazing organizational quality about it, and we're going to talk about that today. So first we're going to talk about metals versus nonmetals. As you know, metals are going to be on the bottom left-hand corner. So this is the highly metallic side. And this is the most non-metallic side. Non-metallic. Right over here. So the closer to the upper right-hand corner you are, the more non-metallic you are. And the bottom left, the more metallic you are. So the two corners of the periodic table here and here are the extremes of every property that we're going to discuss. Okay, now we're going to talk about size. The smallest size element on the periodic table is going to be right here, smallest size, and that's going to be helium. So the smallest size is helium, and the biggest size is francium. Now you may understand why as we go down it gets bigger, and that's because you have more electrons. So the more orbitals, 1s, 2s, 3s, 4s, you're getting bigger. But what might surprise you is that as you move across you get smaller, because there are more electrons as you move across, and it might be a little confusing. So what we're going to do is we're going to take a quick example down here on this chart. Let's, for now, just compare fluorine and neon. Okay, the first thing we do to compare size is always going to be to look at the energy level. So if you have lots of energy levels, you're going to have a bigger size. So if you look at the energy levels of F, it ends in 2p, 2p5, and neon ends in 2p6, so they both end in 2p. So their energy levels are the same. So now what you do is you look at protons. Now remember, protons are positive, so because they're positive, they attract the electrons. So the more protons you have, the smaller your size, because the protons are attracting the electrons and pulling them in closer. So this fluorine has 9 protons versus neon that has 10. So since neon has 10 protons, it's more attractions, so neon will be smaller than fluorine. Okay, if you look back at the periodic table, you'll see that fluorine is somewhere over here. Fluorine is over here, and neon is over here. And neon is smaller, we said, than fluorine because it has more protons. And you only compare that if they end in the same level. So hopefully now you understand why as you move across the periodic table you have a smaller size. It's because as you move across there are more protons in the nucleus and you still end in the same energy level, and so you're going to get smaller. Okay, now we're going to talk about ionization energy. Ionization energy is the energy required to remove an electron. So ionization energy, the highest one again is going to be helium. In other words, it costs you a lot of energy to take an electron from helium. So I'm going to write a little note here that the currency of chemistry, and let's pause for a second. If you went to the store and you want to get some gum, you have to bring money with you because you have to pay money to get the gum. Versus if you were babysitting or mowing a lawn or doing any other job, you get paid because you're doing the work. So the currency of chemistry is energy. If you want jobs to get done, it costs energy. So if you want to take an electron away, it's going to cost you energy. So ionization energy of helium is the highest versus the lowest ionization energy is going to be the francium corner. Because francium is such a large atom, it's going to be easy to remove an electron from francium because it's so big. The electron is far away from the nucleus. But because helium is such a small atom and it's a noble gas, it's really hard to take away an electron. Therefore, it's going to be a high ionization energy. Okay, let's talk about electron affinity. It's the complete opposite. Now, the atom is getting an electron and paying you energy. So again, this corner is going to have the highest electron affinity, but it's not going to be a noble gas because noble gases don't want to gain electrons. And you would think it would be fluorine because that would really want to gain an electron, but actually it turns out to be chlorine in real life. And what happens is as you go from fluorine to chlorine, you're pretty much doubling your number of protons. You're doubling the number of protons. I guess I'll write it the other way. So that is going to really double that positive attraction for the electrons. And so it makes up for the fact that it ends in a higher level and it's still 2 times the number of protons as fluorine. It still attracts the electrons more when it gains an electron. So the highest electron affinity is going to be chlorine, and the lowest is going to be francium corner. Okay, and then lastly we're going to talk about electronegativity. Electronegativity, these definitions are on the second page of your notes, by the way, is the attractions for electrons in a bond. In a bond. When they bond, it attracts the electrons more. So fluorine is the highest, and the lowest, again, is going to be the corner by francium. So let's talk about each of these one more time, okay? Ionization energy. Ionization energy is the energy required to remove an electron. So I'll write an equation for that. Let's talk about an easy one like sodium. All right, sodium, if you give sodium energy, you pay it energy, it becomes sodium plus an electron. It gives you an electron. Okay, versus electron affinity is, if I give you fluorine, let's say, let's do chlorine since that was the highest one. Chlorine, whoops. So we'll do chlorine here. So now electron affinity means chlorine is going to get an electron. The word affinity means to have a love for something. So chlorine gets the electron, so it becomes Cl minus, and it pays you energy. So see, this is energy is being released, the electron is being absorbed. Here, energy is being absorbed, and the electron is being released. So they're opposites. Okay, and lastly, we're going to talk about shielding. Shielding means the outer electrons are shielded from the nucleus because they're so far away. The other energy levels in the way shield them from being attracted. So the bottom of the chart has the highest shielding and the whole periodic table, but it doesn't change as you move across because you still have the same energy level as you move across. So shielding is only different at the bottom of the periodic table. So now let's finish up this little chart down here to help us understand the trends. Okay, and we'll do size. We're going to compare atoms and ions. Okay, an atom and an ion. Remember that an ion has a charge and an atom does not. So this is an atom because it has no charge. This is an ion, it has a charge. This is an atom, it has no charge. This is an ion, it has a charge. This is an atom, it has no charge. Let's fill in all the last orbitals of these. This ends in 3s. This ends in 2p because it lost an electron, remember. So now it's a 2p6. And this also ends in a 2p. So if we're talking about size, you could see right away that the sodium has to be the largest because sodium is going to end in 3s, and that's a higher orbital than all the other ones. So once you're done with that, just don't even look at that anymore, okay? We're done. We're not looking at sodium at all. Now we're going to go for protons to look at attractions. So this has 11 protons, this has 9, like we said. This still has 9, and this has 10. So we have all the protons right here. The more protons you have, the smaller you are. So this is the smallest one, and A plus has to be here. And then we've got neon, so this is done. This is next, neon is right here, and then we have the last two, they have the same protons, orbitals and the same protons. So now we're going to look at electrons. Well, let's talk about electrons. The more electrons you have, the more repulsions you have because they're all negative, they repel each other. That's going to make your size larger. So more electrons means larger size. So this has 9 normally, but if it gains when it has 10, because of this negative sign right here, and so more electrons means it's bigger because it has more repulsions. So here's your F minus, and here's your F. So to summarize this, whenever you are given a bunch of elements in either ions or in atoms, you have to compare their levels, their protons, and their electrons in that order. First, compare level. If the level is different, the higher number is the bigger atom. So that's why sodium was the biggest. If there's a tie with the level, then you go to protons. The more protons you have, the more you attract your electrons, so you get smaller. So this is the smallest, followed by neon, and then you have an F and an F minus. And then lastly, if you have energy level and protons the same, you're going to look for electrons. And electrons, the more electrons you have, the more repulsions you have. So this has more repulsion, so it's bigger than that one. And that's going to compare the electrons for the size as a last comparison. Okay, we talked about shielding, that you can't attract your outer electrons due to repulsions of the other electrons in between. And we said that that happens very often with the bigger atoms like francium, because, and this whole row, because there's so many levels in the way. And then we'll continue the notes on the next page. Now we're on page 2 of the Chemistry 1 Chapter 6 packet, and we're going to continue talking about ionization energy. We're going to talk about the ionization energies of manganese plus 2. So we're going to start with writing the electron configuration. You need to be able to do this by yourself with just a periodic table. So you would go through the order here: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. You can substitute the beginning of this with a noble gas configuration of argon. You have to use a noble gas. You can't just pick any random element. So you'd write argon and then 4s2, 3d5. When you want to remove electrons, this plus 2 means you're losing 2. You always lose from the highest level. So 4s is a higher level than 3d, even though 3d comes after 4s. All right. Now let's try to look at, oops, not the, sorry about that, not the 3d, just the 4s. Okay, so now we're going to look at the plus 3 ion for manganese and see what happens there. Again, we're going to write the electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Again, you can substitute up to 3p6 with an argon configuration, then a 4s2 and a 3d5. Now we're going to lose 3 electrons altogether. So we're going to lose 2 from the 4s, but then we're going to lose 1 from the 3d as well. The analogy, like we talked about with the 4th graders and 3rd graders, all the 4th graders got to go on a field trip. There was 1 extra seat, so they took 1 of the 3rd graders. But you have to take all the 4th graders first. So that's going to be the configuration for an Mn plus 2. So don't be that person that forgets to take it from the highest level first. Now we're going to talk about why the periodic table is called the periodic table. You see the word period in the word periodic table, and a period is something that repeats, an event that repeats over and over again. For instance, if you were going to go to your first period class, your teacher says, "Good morning, let's take out our homework, here's a new lesson, here's a new homework, have a nice day." 5 minutes later you go to your next period class and the same thing happens. "Good morning, take out your homework, here's a new lesson, here's your homework, have a nice day." So hopefully your day actually is not quite like that, but that's what period refers to. So if you're going to look at the periodic table, you'll notice that as you move across the periodic table, you're going to have a repeating pattern from an alkali metal here all the way through all the properties to a noble gas, which doesn't react that much. And then boom, all of a sudden you're an alkali metal, which is actually very reactive, all the way to a noble gas again. And so we're repeating periods. Every row on the periodic table is called a period. So now let's take a look at what that means for the graph below with some exceptions. So you can see on this graph that there is a trend that repeats itself, again, like the periodic table. So you have hydrogen here, and then you go to helium, and the helium ionization energy is very high. It's very hard to take away an electron from helium. Then all of a sudden it becomes very easy to take it away from lithium, and then it gets harder, harder, harder until you get to neon. And this is a repeating pattern throughout the periods of the periodic table. You'll notice that the higher ones are the noble gases, because it's hard to remove an electron from a noble gas. And it gets easier, though, for you to remove it from the bigger size noble gases, because the electrons are farther from the nucleus. So, but they're still the peaks, and then the valleys are all the group 1 alkali metals. But there are some exceptions, and let's take a look at that briefly together. So we're going to start with magnesium and aluminum. So magnesium and aluminum come over here after sodium and after sodium is magnesium, then aluminum. So what does magnesium look like? Magnesium has a 3s2 last orbital, whereas aluminum has a 3s2 and a 3p1. So you'll notice that generally the ionization energies are increasing as you move across the period on the periodic table. As you move across, they're getting harder to take away. But the interesting thing is that aluminum, which comes after magnesium, is easier. So let's talk about why. It's easier to remove an electron, as you can see, because you are ending now in a filled 3s orbital. So because you're ending in a 3s, it's fairly stable. Versus here, you're disrupting a filled orbital, so it's harder to remove that electron. So it's harder to remove electron because you're disrupting a filled 3s orbital. Okay, let's move this up and go to the next exceptions. The next exceptions have to do with nitrogen and oxygen. Sorry about this. I don't know why I did that, but anyway, nitrogen and oxygen. So let's take a look at those. This right here is going to be nitrogen, and this right here is going to be oxygen. So why is it difficult, or shall we say, why is it easier to take it away from oxygen? So nitrogen ends in a 2p3. Oxygen ends in a 2p4. So if you're going to remove an electron from oxygen, it's a little easier. It's easier to remove the electron because you are minimizing repulsions. Repulsions. So here's the analogy again with the school bus. You got 3 benches on a school bus. They each fit 2 people. This is 1 stranger in each seat. This has 2 strangers in the first seat. So there's a little bit of repulsion going on here, a little bit of awkwardness because they don't know each other. But if this person leaves, it becomes very easy for this person to leave because now each stranger can have their own bench. So it's a little easier to remove an electron here because of the because you are minimizing repulsions. However, this one already has minimal repulsions. So there's nothing special about that one. Whenever you're half filled, you have minimal repulsions. Okay, let's move this up to the next part, and we're going to see what happens here when we have this drawing of ionization energy. You'll recall that sodium is in group 1. So group 1, it's going to have 3s1 for sodium. So I'll put that over here, 3s1. Let's do this first. So 3s1 is what it has. So when you lose an electron from sodium, you're only going to lose it from the 3s, and that's pretty easy. So it's about 496 kilojoules. But let's suppose that you were going to take another electron away. Well, that has to come from the level below, which is 2p. And this 2p is completely filled. So it's going to be very difficult to take away this electron right over here. So see how this is like 10 times greater. Okay, but if you had magnesium, which is in group 2, you could see that this has 3s2. So taking 2 electrons away is going to be, you know, following an equal pattern. But then when you get to this, there's a big jump. So you could see from here to here, it's kind of like a ×2. From here to here, it's ×4. It's, you know, it's big. So that's a big jump. If you look at aluminum, which is in group 3, it's easier to lose 3 electrons from aluminum because it would lose it from, let's say, the 3p. Has a 3p1. So it could lose this electron right here and these two, and that would be 577, 1800, 2800. You know, it's following an relatively equal pattern, but this jumps up to 11,000, which is a huge jump. So you can see the huge jump comes when you start to remove an electron from the level below. So this chart is a little clue to what group an element belongs. So if you see an element that loses 1, 2, 3, 4, 5 electrons, you know, at a fairly constant pace, but then this 6th electron is really, really hard, that means that it must be in group 5. So this tells you to which group an element belongs based on these large jumps in ionization energy. Group 7, and lastly group 8. Okay, and as we look at this, you could compare the ionization energy, the second ionization energy of sodium with the second ionization energy of magnesium. Here's the second one of sodium. Here is the second one of magnesium. So this one is a lot higher because you are disrupting a noble gas configuration. This is not really writing very well, I'm sorry. Anyway, noble gas configuration. And this one is going to be a little lower because you are getting a noble gas configuration. When you remove this electron right here, now you're losing those 2 and that's it, and then you're ending with the 2p. So I'm going to write because you're attaining a noble gas configuration. All right, and then we're just going to do the last couple points right here. Oh man, trying to move this, it's not cooperating. There we go. Move that. Kind of move separately here. Let's get this. Okay, let's just do this real quickly. The energy absorbed, or the energy absorbed by a gaseous atom or ion to gain an electron is electron affinity. Remember, I told you it's always going to release pretty much, so that means it's released. It's going to be negative. So the definition says absorb, but if you list it as a negative number, that means it's absorbing negative energy, which means it's releasing it. So it gives away energy to gain an electron. Electronegativity is attraction for electrons in a bond. So if you have something like chlorine, which if it bonds with another chlorine, it's going to share exactly equally because they're both the same element. So they have the same electronegativity, which is a pull on electrons. But if you put H with a Cl, Cl is much stronger in electronegativity because it's closer to that upper right corner. And so you're going to see that the electron is not shared equally, but it's going to go much more towards the Cl, and that's because it has a much higher electronegativity, which is attraction for electrons in a bond.